Well, thanks very much for the invitation. And I've really enjoyed the conference so far. The only problem has been that it's kind of made me rework my slides the whole time, because this is not the kind of conference I typically go to. I wasn't sure how to frame this as a computational thing, but hopefully. So I wanted to start off by just saying that we're really in a new era of astronomy. I mean, I guess every era is a new era. But right now we've got absolutely huge surveys going on. I work at an institution that does SS and probably with LSST in the future. There's Gaia, there's SKA, and those are all things that instead of looking at an object and writing a paper about an object, you look at millions of things, millions of galaxies, millions of stars, you're measuring something about them and you're really data on them. The SKA, just to terrify people, is going to produce an exabyte a day of raw data if you wanted to store it all. They're only going to store about 300 petabytes per year. That's the design I saw at least. They could maybe do the analysis on site, but they would need probably a nuclear power plant directed straight into the computer just to get the processing power. We're not quite there yet. Like Alex said, we basically have audio data. LIGO's a podcast at a pretty good, not that high frequency. But it gives us a new window on the universe. Gravitational waves can't be blocked. They're produced in a totally different way than the rest of astronomy, so we're learning something that's totally orthogonal to what we knew before. And it's of precision. I don't think anyone said this yet. We never actually talked about how big these gravitational waves are. In physical terms, the displacement that they're causing is smaller than a proton. 100th the size of a proton. And 4-kilometer detector. And so what we have is an incredibly complicated instrument that's quite expensive and is the first of its kind. So we have to keep it healthy. And we also have to be able to trust what it gives us. So the plan of the talk is basically I'm going to tell you what is data quality because, I mean, it's kind of our term. We also sometimes call it detector characterization interchangeably. So what am I actually trying to accomplish? Then I'll talk about the instruments and the data that we have. So, what resources do I have to accomplish what I'm trying to do? And then some of the algorithms that we use. And we're kind of stuck on, we're in a sort of an old field in a way. I mean, LIGO's been worked on for maybe 30 years. So we've processing domain knowledge that we've been using. And now we're transitioning to big data, machine learning, that sort of things. So the algorithms I'm going to show you are actually made more for interpretability and simplicity than they are for big data, but we're really moving that direction. So I'm going to try and maybe talk about how we're going to advance in the future. So we basically have three things that we want to do. So Alex is doing the search. So I was doing the parameter estimation, following that up. And especially needs to know when it shouldn't look at the data. When is it going to get fooled? So we mark all the times that the detector is misbehaving. This is a failure of some radio frequency modulation system. And you can see at the bottom here, let's see, which one is the laser? Yeah, at the bottom there, you're marking all the times when it's gone bad. And sometimes it's just bad enough that you should ignore anything you see there. And other times it's bad enough you shouldn't even try to analyze it. Like there's no hope. I don't want to install Chrome, thank you. Yeah, well, hopefully that won't happen too much. Even better, if we can hunt down the causes and fix them, that's the best thing that we can do. Instead of marking them, we just want to actually go back to the people who work at the instrument and say, this is what's wrong. And you can't see it on this one, I'll come back to this, but there's an actual prediction overlay with us showing that we actually know here, but I'll come back to that later. So that's the second thing we can do. And the third thing is when we have a detection, we can validate it. We can say, we know that the detector, we know how it behaves, we know it can't do this, we know that the background estimation is correct. We know also that there wasn't any at the time. Or if there is extra noise, this is that binary neutron star, and we've actually cleaned out of here this gigantic honking, what we call a glitch. The detector misbehaved, but we had a way of dealing with it because we'd seen it before. We knew what happened. We knew that it doesn't affect the detector more than a fraction of a second outside the time. So we were able to deal with it. because we knew our detector. Okay, so let me just quickly go through match filtering. It's basically the key to the most interesting discoveries. Everything we've made has been with match filtering. There's a few things that are sort of unknown searches, and they're similar enough to match filtering that a lot of what I'm saying applies to them too. So we need Sasha's talk, forms in the templates. We need to search over all these unknown parameters. That's what Alex was talking about. And match filtering really assumes stationary Gaussian noise. So I love this theorem. I stumbled across it. It's, I guess, from 1938. Is that stationary noise is basically, if you've got independent samples of noise and then you apply an FIR filter, finite impulse response, basically just a bunch of weights where you're taking times and multiplying together, plus a deterministic thing, which in our case sinusoids at known frequencies, that's stationary noise. That is all the model that you need. And it's a really powerful way to think about it. So stationary really means that it's got the data has a spectrum and it's fixed in time. The spectrum's not changing. And it's non-stationary. And then the Gaussian just means that if I were to undo that FIR filter, I would get a bunch of independent samples of Gaussian noise. What that really means is that you're not going to get things that are very loud. Loud excursions are very unlikely. And so match on that fact that loud excursions are very unlikely. E to the minus, basically the square of all the samples added together. That also makes it really naive. If something's loud, it finds it really interesting just because that can't happen in Gaussian noise. So we need resistant to non-Gaussian noise and mark times when it happens. So I think we said that we would show the power spectrum here. So on the y-axis there, I got the strain. That's like the fractional change in the length of the arms. Frequencies, that's the 10 hertz. You can see how the seismic noise is just a wall there. And the gray curve is what we hope to do in the future, probably by the end of the run. So we'll push it down so that at 10 hertz we're actually seeing things. Up here it's shot noise. Someone asked about whether things were fundamental instrumental noises. This is a fundamental noise. This is counting statistics of photons. The way to push that noise down is to get more photons in the instrument. Just like turn up the laser power. Right now we're at 70 watts. 200, you can go up to crazy amounts. And then in the middle there, it's a combination of all sorts of technical noises and instrumental noises, and that's the place where it's really going to be non-stationary. We're most sensitive. We've also got all sorts of things happening. This is just to show the improvement over time. This was the previous runs that we had when we were first tuning the detector, and now we're here, and then we're going to push it further down. So what you can see is that not only does the sensitivity get flatter, you see more and more frequencies. That won't happen forever. We will probably actually have tuned detectors in the future, which are aimed at one frequency range or another. But right now, we can sort of just improve everywhere, and the bandwidth goes up too. So we're really seeing like more of the bandwidth, and that extra bandwidth gives you ability to measure parameters better. Okay, so now I get to show you basically a bunch of pictures of shiny metal and all the instruments. So that's the LIGO site. That's Rattlesnake Mountain, which catches on fire every once in a while. There's some great pictures, actually. We've got an electronic log. You can search for that. And yeah, it's just basically 4 kilometers of vacuum tube that way, and then all the laser and everything is right in there. And so we've already seen this. Basically, we've got test masses at the end of the arms, and we're splitting a laser and measuring the difference in distance masses. But then we've got all these other mirrors that we have to control to basically increase the amount of power from the laser, to basically resonantly extract the signal, to trap the light in the arms. So because we want the arms to be 1,000 kilometers long, not 4, but we can't really build that long on the Earth. So we trap the light in the arms so it like picks up more phase. And then that's how complicated it is. That's most of the important. And so a good instrumentalist or detector characterization person can tell you what any of one of those does. But we've just got all these different photodiodes looking at the light. We've got radio frequency controls, all sorts of things. So it's just, there's all sorts of and it's all really just about this test mass. The test mass is 40 kilograms of fused silica, also known as glass, with a nice coating on it. And it is suspended in so that nothing is disturbing it, except for the wires holding it up. There's 4 actually. And the wires are made of glass as well, so that they have a Q factor of 10 billion. So if you plucked one of those things at 500 hertz, they resonate for an entire by 1 over E. So this is as isolated and as perfect as you can possibly make it. And then you just got system after system wrapped around it. So it is hung on a pendulum, which is hung on another pendulum, which is hung on another pendulum, on a seismic isolation, which is hung on a seismic isolation. Those are both active, which has an external seismic isolation here. And that's pretty much it. Just those. And then control systems everywhere. Step down the chain gets you more and more isolation passively, and also you have controls to get more and more sensitive. And then this is just kind of neat because it shows all the different things we have to deal with. You have 4 different kinds of geophones and displacement sensors on just one of these seismic isolations, 6 degrees of freedom for each one of those. Any single one of those can go wrong. It's got electronics, it's got capacitors, it's got whatever, mice occasionally. You have to be able to find problems in any of those. So just to show what kind of data we're working with, so we have that one channel that's important to everyone else, and then the detector have about 3,000 fast channels, which are sampled at reasonable audio rates. 200,000 slow channels, which are everything from like weather stations to all sorts of control settings. So that's about 1 terabyte per day of data that we need to deal with. It's not huge. It's enough clusters. It is a pain to deal with sometimes. And we've got our own frame format and all that. Historic. And this is just some more of the sensors. We've got microphones, accelerometers, and magnetometers everywhere to monitor problems. So that's the instrument. That's the thing we actually want to deal with. Actually, let me go back to that. So each one of these places that we put something is a place where noise could be coupling into the interferometer, or something could go wrong. So there's so many different things that can go wrong. Now what I'm going to talk about for the rest of the time is basically the algorithms that we have that are going to let us find problems. So I've just picked a couple of my favorites. So let me frame this as sort of a machine learning problem. So the cartoon picture I have of the way machine learning works is you pick a target, something you're trying to optimize. You pick some kind of features, some information that you can feed to it, and then the constraints. Our targets are things like the detection range. How sensitive is the detector overall? How many things can it see? How stationary is the noise? And also transient artifacts, which we call glitches, like try to get rid of those. So these are the different targets we can have, predict these sort of things. Constraints that we usually want, simple answers, interpretability, things that we can deal with, some things that we can understand. And with all those different channels, we have a big multiple comparisons problem, so we have to avoid that. Using physics turns out to be an important thing in all of our models, and the hard thing is to establish causality rather than correlation. I think the talk last night, they were saying that interest in the Backstreet Boys and H1N1 flu are correlated, but probably not causal. Maybe the backwards causality. You get sick and you want to listen to the Backstreet Boys. I don't know. But we need to be able to see things didn't just change. Something caused it, and that's hard. And then we've got the features are all those auxiliary channels, and then various excess power, various different things we can do with the channels. I'll skip through that. Okay. So the simplest, most interpretable thing we can do is lasso regression. So we have, this started out actually, I'm trying to remember how we started using this, but it's kind of evolved the range of the detector as a function of time using all those channels. So one of the reasons that we thought of this, do I have it? Oh yeah, so I have it over there. So times. We would see the range vary on timescales of, well, tidal timescales, because I mean the tides are stretching things and maybe the compensation isn't perfect. We do compensate for the tide of the moon and the sun. And that computer crashes and it stops compensating, you just see the detector slowly sort of slump off over a couple hours and just give up, because that tiny little shift in the Earth is too much. And then we would see it over. So we've got a temperature control system. Things will shift by a degree, and then the range would fluctuate up and down with that. And so what we want to do is to be able to say, okay, just take all those channels, which is kind of a big data problem, like hundreds, correlate them with the range, and don't give me every possible answer. Try to give me a sparse answer. That's why we've got this L1 norm penalty. So that the coefficients will have as many coefficients 0 as possible. Just get a list of the things that best predict the range. So this is what the page looks like, and it'll give you coefficients. And then here's an example. I'm actually not sure of. This is one of those causality or correlation things. Are these just correlated, or is it telling me something? We've got that. That's a heating time scale, I think. Yeah, tens of minutes as the heating turns on and off, and the range will fluctuate up and down with it. 5 million light years of range that we're switching by, how far we can see, basically. And then we get a list of other channels that are correlated with it. I think I've cut off the plot there that shows what their names are. But this is trying to tell me what is actually causing it. And then the thing I was really happy to see, at the end of the first science run, the detector lost 10 megaparsecs of range. So that's 30 million light years, if I have that right. That's pretty huge. Our range back then was about 60. And we finally figured out what it was at the end of the run, and we wanted a way, when this happens again, to find it. So what had actually failure. At one of the ends, we had a computer monitoring a temperature. The computer had a little bit of electronics fault. It would start to register the temperature wrong, which was just a signature of the computer was making extra noise, and that would couple in. So just one computer that's not even important, and the little bit of electronics noise in it couples in and ruins our sensitivity by 10 megaparsecs. That's how sensitive we are. And what happens is it failed at some point, but before that, it would switch states. You would see that the computer had failed, and it was registering the temperature wrong, and the range would jump because the noise was there. And so this thing would search through these 200,000 channels and tell us that that was happening. And so that month or two that broken detector, we could have totally avoided if we had this. So that's sort of our first example of something that we do. Switching gears quite a bit is something called Gravity Spy. So this is a citizen science project. You may be familiar with some of these other things. So it's basically getting people, volunteers, to go and help you do your science. So you build a training system for them, they go to a website, and they classify things. In our case, we're classifying images. So those images I've shown you of the detector are recognizable to an expert, and we teach citizens, volunteers, to recognize them. So here's what it looks like. This is called the whistle. It's a radio frequency artifact. Learn how to distinguish this from other things. They go through and we did a couple hundred to train them. They do 1,000 and then they've done thousands. And then we feed that to machine learning, and machine learning uses all those classifications to get better. Learning takes more things and gives them to the volunteers with some idea of what they are. And it's kind of an iterative loop where the machine learning will help them to improve themselves. And of course, it's a CNN. I mean, it's basically just an image problem. And then we even have a chat service where they can talk to each other and invent new things. So this is some gremlin that I've never seen. I know most things that the detector does, or I used to at least. And now they'll come up with names for this. They'll tell us about it. And then we're also working on a similarity search so that the machine learning can kind of learn how things are similar, and then bootstrap this. So give them things that they can work with. classifications to try. Right, so that's, so let me, I mean, the slides will be available online, so if you want to find Gravity Spy, it should be easy. Yeah. So last thing, for the seismic noise, the ground is always moving at a micron a second, which is huge. We suppress that by 10 orders of magnitude, but the mirrors are still moving. It's the biggest amount that the mirrors, that's the dominant contribution to the mirrors moving. So as they swing back and forth, what happens is some of the light scatters off the mirror, bounces off anything, bounces back into the beam, and as it hits something that isn't moving with the mirrors, I shouldn't say it that way. The mirrors are like sitting there in space. The Earth is moving, and the mirrors are basically, if you imagine it, they're sitting there, and the Earth is moving around it. But then that means the parts of the detector are moving too. So what happens is that scattered light has an extra phase, isn't part of the main light, and you get these arches. As the mirrors swing back and forth, you get a Doppler shift relative. And what we did was we trained a deep, basically another CNN to basic deep learning to just go and predict this based on hundreds of channels, positions, velocities of the mirrors, and try to find, try to do anything to predict when this was happening. And then what we do is we go back and we look at the most interesting things, iteratively sort of defeated it. We would take this trained model, take out some of the information and train it again, or just take some of the information and scramble it. So you just give it the same distribution, but scrambled so that it's at the wrong times. If it can still predict, even if it doesn't have from one mirror, that mirror is not the problem. So we tracked it down to a couple mirrors at one end station, and we were able to predict the motion. And then we can use that neural network to basically, this is that scattering noise there. And then if you just remove all the times predicted purely by this, it just drops off to almost nothing. So you can see it just sort of goes away. And I mean, we hope to be able to do even better. And then we can do this to the search. We can actually just remove those times from the search and try to make it more sensitive. But even better, we told people at the site what was happening. They figured out how to make that mirror. They didn't make it not move, but the scattered light didn't hit it, and it just it stopped happening. This is a much harder case. This is something where, and this is basically where I'm going to conclude with future work. This is mostly using few combinations. So the first time that we've really you used all the mirrors and just put them together. So you've got thousands of channels all feeding in, and then it will just it uses a combination of a couple. One mirror doesn't predict this, so one channel doesn't help. You need a lot of information. But it's not the whole information about info. This is something where no one sensor can actually see this. This is the same sort of mechanism, but it's much more internal. There's an internal baffle that moves. And so to predict this, we're going to need something that can actually take a bunch of sensors, fuse them together, and figure out internal to the detectors moving, and do something we haven't done before. I'll skip over this last one, but this last one is great for actually getting rid of those whistles, just by looking at one at a time, like one of the channels. And looking for deviations from the normal behavior. So yeah, just to conclude, what I'd really like to do in the future, and we're still, no one has one of these detectors. We're building it as we go along, and so no one knows how to deal with one of these, and it gets worse. And the detector's getting better and more quiet in some ways, but then that uncovers new noise sources. It uncovers the fact that the lights on your GPS unit blink when it's synchronized, and it's synchronized. So you get a 1 Hertz frequency on your data from that light blinking. A little LED drawing power, shows up not very strong in the data, but it's there, and the pulsar search sees it. So we really want to try to integrate these ideas together and use all of the data to machine learning, but still try to keep interpretability. That's the big thing. Like, we want to be able to understand what it's doing. And just some concluding thoughts. The infrastructure is really important. The reasons I can't do this exactly what I'd like is it's still hard to access our data. It's only hundreds of terabytes, but it's on kind of a small cluster, and so, I mean, we really need better ways of getting at our data. Expert knowledge and signal processing with machine learning are really powerful. And all the big science projects that are coming up with very sensitive detectors should be thinking about data mining diagnostics from day one. It should be built in, like I know CERN has done, and now we're trying to do.